Swayam Prabha. Digital India. Educated India.
Welcome back, students. So, in this lecture, we will look at operational amplifier as a black box. We could do this particular class in a variety of ways, but I thought this would be the most interesting way of doing studying analog circuits. So, initially, I would like to expose you to operational amplifier, what operational amplifier as a black box behaves like, and what are the different non-idealities that we see in the operational amplifier, its impact on the circuits. And the main reason for this was there used to be a associated lab in the afternoon, so you could whatever you have learned in the classroom, you get to play with that when you go back to the lab. So we will continue doing that because we found that students really like that approach. Even though you don't have a lab, or many of you who are listening to this on the satellite program, you're not doing any lab, but I will try to show you variety of things which are almost like a lab experiment. Okay, so let's see how that goes. Give us the feedback if this method works better for you. So in today's lecture, as I said earlier, we are going to look at operational amplifier as a black box. Now, what is operational amplifier? So as the name suggests, operational amplifier is a generic multi-purpose amplifier that can be used to do a variety of functions. Now, it could be adder, subtractor, amplifier, differentiator, integrator. So all sorts of mathematical operations we should be able to do using this operational amplifier. So initially, when we were building transistor level amplifiers, then it was difficult to make large circuits with these transistor level amplifiers. So then now there is this operational amplifier as a black box that you could purchase, and that could be done by different companies, and they would be pin compatible, and using that operational amplifier you can create many circuits. So operational amplifier is kind of like as I like to call it, a sub-circuit which contains whole bunch of transistors, and it behaves in certain way. And that operational amplifier you can plug into different circuits to create different functions. So in this part of the lecture, we will discuss operational amplifiers in detail as a black box. So let's get started. So let's look at what I'm going to do is I'm going to take you to a website first, a commercial website, and let's look for a really famous operational amplifier which has been used in many applications. The name of the amplifier is 741. And this amplifier was designed by David Fulager in 1968 when he was at Fairchild Semiconductors, and then he moved on to Intersil, and finally he founded a company called Maxim. Now this particular amplifier is being used in so many applications purely because of its performance and really simple way to use it. So let's explore that amplifier online first. So here is I just typed up LM741, and this one is from Texas Instruments. Now many times these chips are also called like a jelly bean chips, which means that they are like a fundamental components which can be used to put together a whole bunch of other circuits along with it to create complex circuits. And using these operational amplifiers, your design becomes, the process of doing a design becomes very simple. So this LM741 amplifier, you can look at the website, and this is something called a product brief or technical document for that particular amplifier. So this you can, if you go online, and this is one of the configuration where this amplifier can be used. And as I said, this the LM740 from the triangle that we talked about is what we're going to study today. Not just LM741, but we're going to talk about a generic operational amplifier. And here you can see there is a positive supply, there is a negative supply, and we're going to talk about that. So this amplifier generally comes in different packages. So there is a circular package, LMC package, or it can be like a rectangular chip package. And then if you look at the package, it will tell you which pin corresponds to which terminal on the operation amplifier. Then there are absolute maximum ratings which are specified, so you should never exceed those, otherwise the manufacturer will not guarantee the working of the amplifier. I mean, you can cause damage to the amplifier and they will not replace it. So those things you need to follow. Also, there is like a whole bunch of electrical characteristics, which is like a performance of the amplifier, minimum and maximum number, they are specified, the electrical characteristics are specified. So we are going to talk about all these things. How do you read all that stuff and understand what is the implication of each one of them. And you should be able to, once you understand the limitations or non-idealities of operation amplifier, which we will do in a follow-up lecture, you will be able to make a different, depending on the application, you can choose different types of amplifier, operation amplifier. Now this particular diagram shows, so this amplifier is created using BJTs, bipolar junction transistors, and you can see there are NMOSs, you can see there are NPN and PNP transistors and resistors and some capacitors in this particular amplifier. So once the amplifier is done, then you don't have to go inside the amplifier, because it will behave as a black box, as a model, the same way every time it's being used. Then there is a waveforms when the amplifier is being is used. It shows, and then generally there is some kind of layout example that is specified. Now in this particular case, just wanted to bring it to your attention. The rectangle with a semicircular cut is actually the chip package part of this amplifier, and if you see that black dot, that represents pin number 1. So that uniquely represents pin number 1, so that you don't flip it around and make a mistake. Okay, so and that way, once you have an example PCB layout, you can put this amplifier on top there. All right. And there are mechanical specification of the amplifier, how this is going to look like, so that you know how to mount this amplifier on a PCB. Okay, that's it. So as I said earlier, operational amplifier is a multi-purpose amplifier. And it can perform various operations, such as adder, subtractor, amplifier, or you can do differentiator, integrator, etc. Okay, so when you buy the amplifier, it may look something like this. I'm just going to quickly draw the 3D picture of the amplifier so that you can visualize it, and then something like this, and then you will have few pins coming out. So in this case, there are totally 8 pins. And these 8 pins will be, these are the ones pieces of metal which you will solder down on the board. So you will have some on the other side too. Okay, so So you get kind of visualize this whole thing. And then generally there is a dot over here. That means this is pin number 1, 2, 3, 4, and then it goes this way, 5, 6, 7, 8. Okay, so that's a generic convention. And in this particular case, we were talking about LM741 amplifier. So it's wired like this. So there is a triangle which is showing the amplifier. It has two inputs, positive input and negative input, that is connected like this. Maybe I should use a different color so it's easy to see. So let's use yellow for this. So positive input is connected to this one, negative input is connected to this one, and then the output is connected to pin number 6. Okay, and then we have, I'm going to use red color for supply connections. So pin number 7 is connected to your, I think it's VDD, and pin number 4 is connected to your ground. Okay, so that's what it looks like. So now, so this is the way, if you buy this particular amplifier, probably few cents or a few rupees, you will get it out there. Next time you come back to our lab, you can also, open it up and check it out in the lab, how it looks like. All right. So when we are doing circuits with it, this is the way it's going to look like. So we will draw the circuit like this. Okay. So you will have plus, minus, and then you will have supplies. Okay, so this is called VCC, VEE, and this is your output, V output, and generally I like to call this is VP and VN. However, different people name them differently. That's okay. One question that I would like to pose to you is, why is this called VCC and why is this called VEE? Okay, and sometimes you also see VDD and VSS. Okay, so let me explain that to you, because that could be a really simple interview question, and it's something that you should know if you're a circuit designer. Okay, so when we use bipolar transistors, okay, in any circuit, then you have a collector and emitter. So generally the collector terminal goes to the highest supply and or towards the highest supply, and the emitter terminal goes towards the most negative supply. Hence the positive supply is referred to as VCC in a bipolar circuit, and negative supply is referred to as VEE. Okay, and similarly if you are using a MOSFET transistor, okay, so let's say this is an NMOS transistor, then you have a drain region and you have a source terminal. So drain and source, and this is your gate. On this side, this is the base of the transistor. Okay, so generally the drain goes to the most positive supply. So you will, we call for CMOS circuits, generally the supply is defined as VDD, and the most negative supply is referred to as VSS. Okay, just a trivia that you should know, and this you will see it in many places. If the circuit is made using BJTs, then you will see VCC and VE. If the circuit is made using MOSFETs, then it's VDD and VSS. It's just a naming convention. VDD represents the most positive voltage, VSS represents the most negative voltage applied. Okay. Now, one more note about VCC and VEE and ground, okay, and analog ground, because there are so many questions about analog ground that are there in your mind, right? So there is no such thing that is physically identifiable analog ground. Analog ground is for our ease of understanding. Okay, so let me take an example over here. So if you look at the 741, I think it goes, you can apply plus 10 volts or minus 10 volts. Okay, but you could take an amplifier. Okay, and let's say suppose this is supposed to be plus 5 volts and this is supposed to be minus 5 volts. Okay, so this is your VCC and this is your VEE. Okay, so naturally what this means is that the signals which are being handled by the amplifier, they are going to be between these two ranges, okay? And a convenient ground for this particular amplifier will be a 0 volts, okay? So 0 volts, we can call that as ground or analog ground. Okay. Now, when we say analog ground, that means all your signals are around this particular voltage. So in this particular case, it turns out to be 0 volts is the analog ground, because let's say this is the output, and let's say this is 0 volts. Then the signal which is going up and down, it can go up to plus 5 volts and minus 5 volts, purely because that's the way the supply voltage is given for this amplifier. However, let's take another example, which is most commonly used nowadays. Nowadays, you don't use dual supplies, you just use single supply, and in that case, so when you look at the instrument, okay, so this is your instrument which is providing you, let's say, let's take the latest, let's pick a number, let's pick 1.8 volts as our supply, okay? So then you will see plus and minus, okay? And then there will be chassis ground, which will be like this. So typically what we do is we short these two, and this and this, and here on the display you will see 1.8 volts, okay? So this is what you will apply to your amplifier. Okay, something like this and something like this, okay? So the chassis ground, which is where this particular instrument's ground is connected to the earth as a reference potential, is 0 volts here, okay, physically 0 volts. Now when we apply this to the amplifier, now this is 1.8 volts and this is 0 volts, okay, from this instrument point of view. However, when we look at the signals, we cannot really apply a signal with respect to this 0 volts, okay, because what will happen is, if I apply the signal with respect to 0 volts, then if I apply input of, let's say, 100 millivolts at the input, then my negative going peak will be minus 100 millivolts, okay? So this amplifier will not be able to process. So that's the reason we use something called analog ground. And analog ground is something like a reference in our head that we use all the time, okay? So in this particular case, we could say that, hey, let's define VDD divide by 2, which would be 0.9 volts, okay? And that would be our analog ground. Okay. What analog ground or AC ground, or also called AC ground, okay, is the signal is moving up and down around this analog ground signal, okay? So you can put 0 volts here and 1.8 volts here, and whatever signals we are applying at the input and whatever we are seeing at the output, they will be reference to this 0.9 volts, okay? And we call that 0.9 volts for our reference as a analog ground or AC ground, okay? All right. So this will we will be dealing with this many times, and it will slowly become clear to you when we do the circuits, okay? All right. So let's move on to our ideal op-amp. Let's talk about ideal op-amp. What are the characteristics of ideal op-amp? So every time we don't call it operational amplifier, we shorten and we call it affectionately op-amp, okay? So ideal op-amp has, you know, we show it with a triangle, okay? It has one input, second input. So this would be your, this is Vn, negative input, this is your Vp, and then this is your Vout, okay? All right. So negative input is called inverting input, okay? Positive input is non-inverting input. And of course, there is voltage gain between the two, and the voltage gain we specified as AV, okay? This is your voltage gain. And if you look at the model of this amplifier, let me draw the picture for you here. So what we would see is, we would model it like this. So this would be AV times Vp minus Vn. All right. So that's pretty much what it is. The amplifier, behaves like this. And what we are doing here is we are, if you look at this particular term, we are taking a difference between the two terms. Okay, and that's why it's also called difference amplifier. All right. Now let me, when we talk about difference amplifier, let me ask you, let me give you an example of why are we really trying to take a difference between the two signals. Why don't we just amplify one signal and then amplify another signal and do something else and subtract them out, right? A good example that you can that I can give you to understand this is an ECG example, or something like any kind of measurement that you do on your body, for example. Okay, so in that particular case, let's say an ECG. I mean, I'm overly simplifying everything for you for the purpose of understanding. But ECG, in when you're measuring your heart rhythm or something like that, you're actually taking a difference between the electrical impulses at two different positions in the body. Okay, so for example, let's say this is your heart, and then this is your leg. Okay, so somewhere close to the leg. So I want to take this difference and I want to take this one. I would like to amplify the difference between these two. So let's say we just did one amplifier like this and one amplifier like this. Okay, and then we said, okay, I will now take a difference between these two by adding another plus minus subtractor and something like this. So this example would illustrate this difference amplifier functionality of the op-amp. So the signal, let's say we connect one lead towards the heart and one lead towards your leg, let's say. So if you, I'm sure all of you have played with an oscilloscope before, and I'm sure you have touched the lead of the oscilloscope. So if you touch the lead of the oscilloscope, you will see there'll be like a really large signal that's going on like this, right? And if you keep playing with the oscilloscope, you will see a 50 hertz type of tone or a 60 hertz type of tone, depending upon which country you are in. So that and that's a pretty large signal that you will see that's there riding in your body all the time, okay, because the surrounding you are in. Now, the kind of signals we are trying to detect, for example, between heart and your leg, for example, to do an ECG would be really small signal, so which could be less than a millivolt. And here is something like 50 to 100 millivolts of 50 hertz hum, we call it, or that's riding on each side. So let's say there is a 50 hertz tone here and there is a 50 hertz tone over here. Okay, so these are large signals, okay, which are large and noisy signals which are on each lead. Now, if we amplify them separately, then our desired signal which is going on is a small signal that's riding on top of this signal. And so when we want to amplify, we have to amplify both sides. So we want to make sure that this particular amplifier and this particular amplifier has a very large dynamic range. So it should be able to handle the small signal as well as the really large signal that comes along with each lead, right? So this is very inefficient. So instead, if we have a difference amplifier that we just talked about, which can do something like this here, Vp minus Va, and then we can simply take these two leads, and then we can use an operational amplifier type of circuit, and we can subtract them out right at the input itself, so that the common mode signal, as I like to call it, because this is a common signal to both sides, does not get amplified by the amplifier, and only the difference between the two signals, Vp and Vn, gets amplified. Okay, so what we would like to see in the ideal amplifier is we have differential input, okay, And then in this particular case, we have single-ended output. Okay. So differential input means the amplifier will process difference between these two signals, these two leads, for example, VP and VN. And single-ended output is just single output in this particular case, and this output will be referenced to some ground. Okay. All right. Now, what is the other feature that we desire is we desire infinite input impedance. Input in this particular case, let's call it input resistance. Okay. We will talk about impedance later stage in the course, but for now let's just say it's infinite input resistance. What infinite input resistance means that there is no current flowing inside the amplifier. Okay, so the amplifier does not load the previous circuit. There is no so it behaves almost like an open circuit. Okay, when it comes to any kind of current flowing into the amplifier. All right. The other thing we want is we want zero output resistance. So what this means is when you have this particular output AV times VP minus VN, and let's say there is some output resistance, right, R out. We want this output resistance to be zero. Okay. The reason for that is if I have some impedance connected over here, some resistance connected over here, we don't want this voltage divider effect. We want this entire AV, VP minus VN to appear at the output, okay, in the simplest terms. I'm going to use a new term now and I'm going to explain it to you. We call it common mode gain. Okay. So what does common mode gain mean? What does common mode signal mean? Common mode means something that's common to both the terminals. Okay, so we are looking for any signal that's common in both VP terminal and VN terminal, and that's what we call it common mode voltage. Okay, so we don't want to amplify any voltage which is applied to both VP and VN. Okay, a common mode voltage. So for example, in our case, the previous example case, here we were applying we were applying to this amplifier the common mode like a AC signal, which is due to our power supply or electrical transmissions, which is 50 Hertz, let's say, and that would be really large. And that would be same on both sides, right? Because it wouldn't change much from one place to another place in the body, and we don't want to amplify that signal. Okay, so the amplifier should reject any kind of common mode signal which exists on both sides of the both terminals, VP as well as VN. And what we would really like to do is then so the point is we want zero common mode gain. The common mode gain should be zero, and of course we want infinite differential gain. So we want AV, which is a differential gain, we want that to be as large as possible, infinite for that matter. Okay. Other thing we also want is we would like the bandwidth, which we will talk at later point in the course, should be infinite, meaning you want it as large as possible. So if you apply 1 Hertz versus if you apply 1 megahertz or 100 megahertz signal, then the amplifier should be able to handle all that. But this is our wish list for an ideal amplifier. Okay, in reality we get different things, and then we try to understand, estimate, and then we try to deal with them in our circuits. All right.